So in the last part, we saw these relations to be true. Phi square equals E and psi cube equals E. I think it would be better if we write these functions down again. I mean, what they do to the elements, because we have some more things to calculate. x1, x2, x3. So phi maps x1 into x2 and x2 into x1. It does not change x3, and psi changes everything, and it changes the things in this way. So it maps x1 into x2, x2 into x3, and x3 into x1. So we can use it to calculate further things. Now we have already seen these relations in the last part. Now from these relations we can derive some things using the fact that S3 is a group. We already know this fact, right? So what are the things that we can do here? Multiplying both sides of phi square equal to E. From the left or from the right, it does not really matter in this case. So let us choose anyone. From the left, say, by phi inverse, we get phi inverse dot phi square is equal to phi inverse dot E. Okay, so this will be true because phi square and E are actually the same element. So if we compose that with phi inverse, we are supposed to have the same element. So that's why this equality. Now what does this imply? Note that we have already seen in the last part that phi inverse actually is phi to the power minus 1, and we have also assumed that the rules of exponents are true. So you can, in place of this, you can write phi to the power minus 1 plus 2, and on the right hand side, using the third condition of a group, we get phi inverse. So what do we have here? This gives us phi to the power 1, and let us not just skip steps. We write phi to the power 1, and then it is equal to phi, so then we write phi in the next step. At this stage, let us not skip steps so that we understand every step of the calculation, why we are getting something that we are getting. On the right hand side, we have phi inverse, and this implies, since we have already seen that in a group, any element to the power 1 ultimately turns out to be that element itself. So we have phi. This is equal to phi inverse. So this relation we have derived starting from this relation and using the fact that S3 is a group. The group axioms can be used in this way to calculate with group elements. Okay. And in a similar manner, similarly, from psi cube equal to E, we get psi square is equal to psi inverse. Here also you multiply both sides of this equation by psi inverse, either from the left or from the right, that does not matter, that will ultimately give you this, using similar conditions that a group satisfies. Okay, now so you see that the elements phi and psi that we have considered in S3, their inverses turn out to be these elements. Inverse of phi is phi itself and inverse of psi is psi square. So let us now calculate, apart from these things, two more elements. Next, let us compute phi dot psi and psi dot phi, and this we can do just like this one. x1, x2, x3. So when we first apply phi, keep in mind that for us, since we are writing functions on the right, to the right of the argument, so whenever we are writing phi dot psi, we are always supposed to first of all apply phi, and then on the result we apply psi. It always reads in the order, the composition always reads in the order in which it is appearing. First phi and then psi. So when I apply phi to x1, I get x2. On that x2, if I apply psi, then I will get x3. So phi dot psi maps x1 into x3. Phi maps x2 onto x1 and psi maps x1 back to x2. So phi dot psi does not change x2, and since it has to ultimately be again in S3, that is a bijection, x3 must be mapped onto x1. You can verify also, x3 is unchanged by phi, and then psi takes x3 to x1, so ultimately we get to x1, and like that we can calculate psi dot phi. So here first we will apply psi and then on that phi. So first x1 will go to x2, then x2 to x1. So psi dot phi does not change x1. x2 goes to x3, then x3 is unchanged. So x2 here also it goes to x3, and so x3 has to go to x2. So these are phi dot psi and psi dot phi. Okay. Now consider the mappings identity phi psi psi square phi dot psi and psi dot phi. These are 6 mappings, and if you look at them in detail, you will see that they are all distinct. That is, none of them is equal to any other. For example, if you want to, you can see in verifying that they are distinct, you can you can look at it in 2 ways. One is actually looking at the mappings and see that they are doing different things to different elements. For example, if you look at these 2 maps, psi dot phi and phi, then you can see that phi changes x1 to x2, but psi dot phi does not change x1, so they cannot be equal. So directly from these formulas for psi dot phi and phi, you can see that they are different mappings. Another way to verify that they are different is this. Suppose they are not different, then we will have this. what you then do, you multiply on the right hand side by phi. Sorry, I mean phi inverse. In this case, phi inverse and phi are same, so we can multiply by phi if we want. Then you can use the associative law to write this term like this. That this will become identity. This one will again become identity. So that will imply psi is equal to identity. This clearly is not true because identity does not change anything, but psi changes everything. So this is a contradiction. From that you conclude that our supposition is wrong, so they cannot be equal. So in these two ways you can verify that all these mappings are distinct. Okay, one can, we are not going to do that actually here, but I leave it to you to verify. One can verify that these 6 mappings are distinct. But from the fact that G is closed under the binary operation, these 6 mappings must all of them be in S3. I mean by G I mean S3. Since S3 is closed under the operation dot the above 6 mappings. I should probably not wrap this part up. Let us just keep this. Are all in S3. But we already know that S3 has 6 elements. So these must be the 6 elements in S3. We must have S3 equal to this phi psi square phi dot psi and psi dot phi. So using these two mappings we have actually generated all the elements in S3. Okay, now one can ask, for example, what is the entry? See, according to the closure property, if we take psi inverse and compose it with phi, this again has to be in S3, but which map is it? That, suppose someone is asking that. Let us now try to see what map it turns out to be. Suppose we ask which among the above 6 maps or mappings equals psi inverse dot phi. We calculate it for our ease of calculation. Let us first of all write just psi inverse. Psi takes x1 to x2, so psi inverse will take x2 to x1, so x2 goes to x1. Just like that, psi inverse will take x1 to x3, so that means x3 has to go to x2 because x2 goes to x3. So this is psi inverse. Now we are going to compose this mapping with this one. This is x1, x1. Okay, so first we apply psi inverse on x1, we get x3, and then x3 is unchanged by phi. So let me first write the elements. So we have this. Then x2 is taken to x1 by psi inverse, then x1 is taken back to x2 by phi. So x2 is unchanged, and hence this has to be the case. So you can see that this mapping is actually equal to this mapping. Psi inverse phi turns out to be equal to phi dot psi. It turns out that psi inverse dot phi is equal to phi dot psi. Now besides the relations that phi square equals identity and psi cube equals identity, this is again another relation which we can use to calculate some further products that are possible to in this context. So we can calculate two such things. Let us see. Without writing anything more, we will just simply try to calculate these products, psi dot phi dot psi. You can add okay, before using associative law, we directly use this relation. So in place of phi dot psi, we can write psi inverse dot phi. Now we use the associative law. So this gives us identity times phi from the fourth axiom, and then from the third axiom we get this is equal to phi. So this element turns out to be equal to phi. No matter what you do, what sort of product you form, ultimately because of the fact that S3 is closed under that operation dot, you are going to get one of these things. Okay. One more thing that we would like to calculate is this. Phi dot psi square. Keep in mind what this means. We have already defined in the previous video or in the previous part what integral powers of group elements mean. So there we have seen that this actually means the thing that you know or expect it to be, namely the product of the element two times with itself. Okay, now first we apply the associative law, treating phi, psi and phi dot psi as three elements. Doing that, we get phi dot psi dot phi dot psi. Okay. Now you see here that the thing that we have inside the outer brackets, this is nothing but this psi dot phi dot psi. So that is equal to phi. So this becomes phi square, that is equal to identity. So you can see that once we have found some relations between between group elements, we can then calculate with the other products that are possible to be formed within the group. We don't need to always go down to the actual definitions of the elements or how they behave. For example, we don't need to look at what the functions actually are. The relations are enough for us. So this example shows us how to calculate with group elements. And the example ends with a remark like this. One can similarly compute the others or the other of the 25 products that can be formed and that do not involve the identity element. Twenty-five products because there are 6 elements. Now if you choose any 2 of them randomly, then actually 36 products are possible, but in such choices E will be there, the identity. So if you remove that, then you have 5 square choices, so 25 products. You can calculate if you want such products. We have calculated a few here. So like that you can calculate the others. Every time you do, you will see that you end up with something again in S3 because of closure property and because of the fact that S3 is a group. Okay, so here that the third example ends. Now we look at example 4. So example 4 is a familiar one, but still let's see. Let n be a positive integer. Let G consist of the formal symbols whenever we say formal symbols in mathematics, it means the symbols have the form of something but are not necessarily actually that thing. Here the formal symbols look like powers of something, powers of A, but actually they hold no meaning other than the fact that they are just some abstract symbols. As of now, without saying anything else about this system, or right now we have said only what the elements in the set G are. They are just symbols, that's all. We are now going to impart some or impose some restrictions on these symbols that will give them some meaning. Okay, so the first thing, we assume that a to the power 0 is equal to a to the power n. This is a restriction that we are imposing. Keep in mind that since these are abstract symbols, any restriction that I place on them is going to make the set G shrink. You may ask me, what is the need for calling these two equal? Well, there is a need. I mean, it will become clear when we define the binary operation on G. Right now, what this equality means is that a to the power n and a to the power 0, if I choose to call them like that, actually mean the same abstract symbol. That's what I am additionally assuming here. Okay. Now, we now define a binary operation dot on G as follows. So now we will give the rule for composing elements. For any a to the power I, a to the power j in G, we define a to the power I dot a to the power j to be equal to a to the power I plus j if I plus j is less than or equal to n, and it is defined to be equal to a to the power I plus j minus n if I plus j is greater than n. This is my definition of the binary operation. We will now prove that under this operation G forms a group. Okay, so let us see how that proof goes. There are some things to be proved here. It's not, I mean, we cannot immediately see that it will be a group. One thing that is always particularly challenging while trying to show that a system is a group is the associative law. Since it involves three elements, combination of three elements, so in most of the cases where the binary operation is partly defined like this, showing that the associative law is true generally breaks into several cases. So this is one such example where that will be the case. So first of all, what do we need to do to show that G is a group? We have to first show that this binary operation is a well-defined mapping. Keep that in mind, that a binary operation by definition is after all a mapping. So the fact that we have defined it like this, and that too on a set of abstract symbols, tells us that we need to prove that this is a well-defined mapping first of all, otherwise nothing will make sense. So what do we need to show that this is well-defined? We have to show two things. First, we have to show that whenever we are calculating this quantity, whatever we are getting is again in G, again an abstract symbol in G, and that is not immediately evident because I plus j, here you see we have I plus j, here we have I plus j minus n. For these things to again be in G, I plus j must lie between 0 and n. If it becomes greater than n, then such a thing is not available in G. So that must be verified first of all. And the second thing is that this operation, whenever a to the power I and a to the power j are given to us, then whatever I calculate is unique, because otherwise it won't be a function. So this is the first thing we have to show. Okay, so let us now show that G is a group under this operation dot. For a to the power I and a to the power j in G, we have this. The exponents must lie between 0 and n, then and also they are integers, that is understood. Okay, because that is the range of variation of these things I and j. They can be any integer between 0 and n inclusive. Okay. This implies if we add these two, what shall we get then? Adding two inequalities. Actually, it's not two inequalities, but these inequalities. If I plus j, so you see that already I plus j is a non-negative integer, and we have non-negative integers here in the as suffixes, so that is not a problem. But here there is a possibility that I plus j, it can be greater than n. Then that corresponding, if we write a to the power I plus j without knowing whether it is greater than n or not, then we can't immediately say that a to the power I plus j will be in G. Okay, so if I plus j is less than or equal to n, then a to the power I plus j belongs to G, then there is no problem. But the other possibility is this: if I plus j is greater than, okay, let us write the whole thing. If I plus j is greater than n and less than or equal to 2n, then okay, I think I should have written something else here, excuse me. Then whenever I plus j is less than or equal to n, this product means a to the power I plus j. So this is equal to a to the power I plus j, that is in G. Next, if I plus j is greater than n and less than or equal to 2n, this is the other possibility. Apart from this one, this is the other possibility. Then now if I subtract n throughout, then I will get 0 is less than or equal to I plus j minus n, oh sorry, this will be strictly less than, and this is less than or equal to n, and hence now when I plus j is greater than n, by definition this is equal to this. So in this case a to the power I times a to the power j is equal to a to the power I plus j minus n, but I plus j minus n now again is between 0 and n. So this symbol belongs to G. So we see that the first thing that we wanted to show is actually true, namely that whatever we do, whenever we calculate such a product, the result is again a symbol in G. Now we have to prove that this thing is unique for a given a to the power I and a to the power j. In trying to prove that uniqueness, you will face a problem here, because here we have assumed that a to the power 0 and a to the power n are actually the same thing. So the problem that will arise here is this: if I have, say, a to the power I, and in place of a to the power j I have a to the power 0,